All right, so we're going to do a session on gas, condensate, PVT, and in particular looking at depletion recovery performance. Okay. And one of the things that we're going to do is that we're going to try to show the consistency that you should expect and get when you compare equation of state calculations with a PVT program, simulating a constant volume depletion test, and a reservoir simulator simulating just depletion. That consistency of recovery factor, in particular for the condensate or the oil, is basically the goal. So we're looking at an EOS-based PVT model. So that we need. So we'll have to pick one out. And then we'll have to have a particular surface process that's important to define consistently. So this needs to be defined consistently. Between the basically the PVT simulator which we're going to use phase comp, and the reservoir simulator. Which we'll be using sensor. And okay. Let's see here. Because this here needs to be up here as well. In other words, we need to have the EOS-based PVT model defined consistently between the PVT simulator and the reservoir simulator. So we have the same EOS model in both simulators, and we have the same surface process in both simulators. And if you do that for a gas condensate, so if this is done properly, then you should get the following and very important consistency between the PVT simulator and the reservoir simulator. Okay, is that first you should get the same initial gas-oil ratio. We're going to talk mainly about oil-gas ratios, which is just the inverse of that. Okay, in the two models. With the same initial oil-gas ratio, you basically get the same oil in place, the same gas in place, if you will, for the two simulators. More important than that is that you should get the same, and when I say same, it's almost should be line thickness. Okay? Line thickness is almost the same. Because the same to a politician and the same to an engineer is different, right? Okay. The same oil recovery factor as a function of depletion pressure. The same recovery factor of both oil, which I'll write like that, surface oil, as a function of pressure, and it's easier, but surface gas as a function of pressure. For a depletion, and for the man, this is something that's not right or good about the not sure what's causing this to go so slow. So it's going to be using a CVD test for the PVT simulator. And just depletion, blowdown, whatever you want to call it, depletion for the reservoir simulator. And here we're using phase comp, but that could be PVTI or PVT-SIM, whatever you like to use. And we're going to use sensor. Now that could be Eclipse 300 or GEM or whatever you want to use there. Okay. So this is our goal, and I'll just sketch the graphical. What we're going to be trying to create here is this is going to be our recovery factor, which is defined as the oil produced or condensate produced over the initial oil in place, or the cumulative gas. That's processed surface gas, not wet gas or well stream, but it's actually sales gas divided by the initial amount of sales gas in place. And that's a recovery factor from 0 to 100%. And then we're going to have pressure. We're going to have the initial reservoir pressure. We're going to have a dew point pressure. I'll just make a line like that. And then we'll have the gas recovery factor will look something like this. Okay, and that's gas. And the oil recovery factor will look how? What will that look like? Should we pick on Hamid, our guest, or not? You took courses in Calgary?
No.
You took some courses in Calgary?
Yes, I do.
Okay. Did you take any courses in gas condensate related?
No.
Then we don't pick on him. Okay. So how should the oil recovery look? Above the dew point.
There is no oil recovery above dew point.
I hope so. That's where we're making most of our money.
Maybe the oil from the gas.
The oil from the gas in solution. And you have the maximum amount of oil in solution in the gas above the dew point. So we're definitely making money in recovery of condensate. But what should it look like?
It should be constant.
The recovery should be constant? You mean it should look like this?
It should be linear.
No. Okay, let's just look at this. We have a hydrocarbon pore volume that everybody's okay with, right? So basically, if we take, well, that's our reservoir. Put some faults in there. If we take the initial fluid to the surface through some, let's say, just a simple two-stage separation. Okay. Get the gas off the stock tank. Okay. Now this here is what I'm going to call our surface process. That's the way I draw it. P, capital P with 2 lines under it. It's any process you like. We're gonna use a 2-stage, or we maybe use a more complicated, and we end up with, if we take all of the contents of this hydrocarbon pore volume, okay, to the surface at once, that's what the reservoir simulator will do, to tell you how much sales gas is there. This is our sales gas. Okay, and we play God. We just take everything from the reservoir through this process to the surface. And that gives us what? It gives us the initial gas in place. And then we get the surface oil. And that is what we call the initial oil in place. Condensate in place. I call it just oil. Initial gas in place. Okay? That's what we define. And the ratio of those two numbers, okay, the ratio of those two numbers is the initial gas-oil ratio. It's just G over N. Or what we prefer to use is oil-gas ratio for condensates, which is just N over G. For example, with stock tank barrels per million standard cubic feet as an example unit. Okay? Now, what I've said here is that we're getting about, from the initial pressure down to the dew point, we're getting what that looks like, about 20% recovery of this G is being recovered down to the dew point, right? Okay? That's what we're saying. So, from PRI to the P dew point, we're saying that GP over G is 20%. Right? But what is NP? What is the producing oil in the same pressure range? The producing oil can be calculated directly from GP. How? Okay, by multiplying by this oil-gas ratio initial. Why? Because in this region here, the producing oil-gas ratio, which is what we actually have to produce, we have to multiply to get this. We actually have to do this, right? Okay? And I mean, to make it a general statement, we have to do this. Right? DG, basically this would be DGP instead of right. It's irritating. I don't know, there's something going on with the computer here, but this should be the integral, okay? Like that, right? From going at the reservoir pressure, initial, to the dew point. But if you say that in this region OGRP is equal to OGRI, right, then that can just simply be written as OGRI times GP down to the dew point. Let's just call that star. And, okay. Let's see if this is working or not. I may have to, maybe because it's, I don't think this is working. Let's see here. How do you check if it's charging or not? Anybody know how to do that? Okay, so because this is okay for this condition when reservoir pressure is above equal to the dew point, then we get this, right? Okay, so then what is the recovery? What is the recovery factor of oil, which is NP over N, okay, in that region? Well, we can rewrite that as the GP times oil gas ratio initial, because that's the producing oil gas ratio at any time from the first day until you reach the reservoir pressure, right? But what is the initial oil in place? It's G times OGRI, right? So that means that it is the recovery factor of gas times 1, or it's just the same as the recovery factor of gas. Is it clear? Because the gas-oil ratio or oil-gas ratio is remaining constant from the initial pressure down to the dew point. So the curve will be in green here, and it'll look just like this. Okay? But then, as you go below the dew point, you get retrograde condensation dropping out of the gas, and the carrying capacity of the gas, carrying capacity of what? Of condensate drops. That's the little RS term, solution oil gas ratio, drops. And as a consequence, because the only recovery of oil we get in a gas condensate comes from what is being carried in the gas. That's important to remember. I don't care what your rail perms are. I don't care how rich your initial gas condensate is. At the end of the day, bottom line, whatever oil you recover is being carried in solution in the gas into the wellbore. Okay? Now I'm neglecting exactly what the flow phenomena going on around the wellbore, but essentially that's what's going on. So because of that, your amount of oil that's carried in solution in the gas, it's dropping. This is going to look like this. Okay? And the difference between the recovery factor of oil, which has, you know, somewhere between 5 and 10 times the value per mole produced, it's got a lot more value than the gas, is very important, whether it drops off like that, or whether it drops off like this, or whether it drops off like this. Okay? It's very important how it looks, that oil recovery factor versus pressure.
Excuse me, we have to be like this because then we have retrogrades at the low pressures.
No, you never pick up no, you won't pick up at low pressures a lot of this retrograde condensate. Now, the thermodynamics say that if you bring the reservoir to 1 bar, that all the K values of these heavy components are marching their way to very high values. Theoretically, you can vaporize the oil, right? From the K values getting higher and higher. But why don't you vaporize the oil? Why doesn't it? Why don't you get this big kick? Is what you're talking about here. Why doesn't it go like that? Because to get vaporization requires 2 things. Okay? Vaporization of heavy components requires 2 things. What does it need?
Heat.
No, heat is fixed here. The K values need to be high. Okay? The K values of the heavy component, C7. To vaporize C7, you want K value of C7 to be as high as possible. Okay? Because it's saying that component prefers to be more and more in the vapor phase. We go to low pressures, we get high K values. Okay? And it's inversely proportional to pressure, the K value. But that's not enough. That's the desire for that component to be in the gas. Okay? We all know we have lots of desires. We all want to drive a Ferrari to work, right? On a dry, nice, sunny day. Convertible, preferably. But why don't we? Because we don't have the money. Okay? So the capacity to vaporize the C7 is great at 1 bar and 280 degrees Fahrenheit. But you have to have something to vaporize it into. But by the time you reach 1 bar, how many moles of gas do you have? You don't have any moles of gas. I mean, there's a gas phase there, but there's not very many moles. So it saturates with C7. It's done saturated. Once it's saturated, okay, and then what's left is most of the C7 in the oil. Okay? That's why you don't revaporize. To revaporize at a low pressure, you have to inject a bunch of dry gas. Okay. There's a nice paper by Standing, one of the last papers he wrote, Standing and some people in the 1950s, I think, 60s maybe, on gas cycling at low pressures. Now this is what it'll look like, and what we want, this is the type curve of performance for depletion gas condensate. Okay? And actually the laboratory data from a constant volume depletion test gives you this information. Okay? It gives you the information because it gives you the composition and the amount of gas being removed as a function of pressure. So it's giving us all the information we need to create these. So in reality, what we actually have is we have data from the CVD test, and I'll just put that in black. CVD lab data. It's not, it starts at the dew point, but you can correct that to initial pressures. If you read chapter 6 of the monograph, it'll show you how to do that. And it'll basically look something like this. Of course, now I'm gonna go in red, and they're the same, and the red's going to be pretty much in line with what I'm saying our equation of state is. Something like that. It'll go down to about that pressure. Okay, and I'm going to say that the lines we have here, the lines are from our EOS model. And what I'm telling us is that if we use a PVT simulator model with CVD, or if we use a reservoir simulator model with the same EOS, we should get the same line. That's what we're going to try to do this morning. Okay? To get the same performance. So this is either a PVT model or a simulator. And that's the line. But what you may find is that the lab data, okay, the gas is going to be pretty much on, but the lab data might look like this. Okay, so that would be a discrepancy in your equation of state model ability to predict the carrying capacity of the condensate. Okay, so it's over predicting the ability of the condensate of the gas to keep condensate in solution. This equation of state model. That's what it's doing. Or the laboratory data is under predicting because of experimental error the amount of condensate in the gas. If there's a discrepancy there, it needs to be reconciled. So it can be data error, or it can be a bad equation of state, or both. But today's exercise is mainly to try to get consistency between the EOS model. The line should be the same if it's coming from a PVT simulator with a constant volume depletion experiment, or a reservoir simulator with the same equation of state and the same process and the same initial composition. And if you don't get that, then there's something wrong. There's something inconsistent. Okay? The other issue of reconciliation between the data and the EOS model, that's another problem. That's a PVT EOS modeling problem. That's a QC of the laboratory data problem. And those are also issues, but they're not really part of this course. Okay? But we may be able to touch on that briefly. But the point is that there's two lines here on the EOS. There's two lines, and those lines should basically fall on top of each other, which They won't if you don't get things right, if you don't get things consistent. Okay. And if you don't get the depletion performance right, okay, then when you're doing this course's EOR, then you start doing gas cycling and your depletion performance is wrong, then we're just playing games. Okay, we don't want to play games. So this is kind of a basic QC to make sure that you've got the equation of state, the surface process, all the consistency in the reservoir simulator model. And it's very easy to check to compare it with simulation results from a PVT program. Okay, so that's what we're going to try to do. But to do that, we have to have this consistency that I started with. We have to put in the numbers, the equation of state numbers right, we have to put in the compositions right, and we have to put in the viscosities, maybe not so important. The viscosity model should be the same, though that doesn't really matter too much. But the surface process is really often the problem in getting it right, wrong or right. So, okay. Okay, so that's the game plan here for what we're going to do. So we need an equation of state. We need to put that equation of state into the PVT simulator. Then we need to put the same equation of state into the reservoir simulator. And then we need to do the two simulations and start comparing numbers. Okay? Any questions about what we're going to do? All right. Then I'm going to start with an equation of state. Let's see here. See, the problem, let's see, the SPE3, I'm just going to go to that. My goodness, that's not what I know. Let's see, SPE3, phase mount files. I'm trying to find one that's consistent with what you've used in the course here. You've been using, does anybody have the data file you've been using here? Let me just pull this one of these up. Now these are the components. Okay. Now to do the comparison, okay, this one has no volume translation. You've already been doing and talking about that. The original didn't have volume shift, right? And you found some volume shift factors?
Yeah, we had the both data files, so we worked on that.
Okay, so I'd prefer using it's with the volume shift. I'm not sure which values you have. You have them in the FaceCom file. I'm just wondering if this is probably not the best data set. Let me see if I can find SP3. Then gas condensate here. This might be. Gas condensate SP3 US. Okay, we don't have the volume shift there. Take the simulator data set. There we go. Okay, so we've got these. So we'll just take, I'll just take these. These should be pretty much the same numbers that what you have. I mean, it's not going to be. So I'm gonna. Let me see. This is. This is the EOR course. PG 8604. Is that right? Okay. All right. Let's see here. We can just look at the simulator data set. We've got 2 alternative surface processes set up. That's good. We'll probably use the C4- and C5 plus in what we do. We've got, I think this is a simple radial model. It's not the 9x9 4-layer. It's just a simple radial model. And then we got the EOS. Here we've got the 2 different ways of doing surface processing. And I'm going to create a little bit simpler model because if you introduce layers, then you start having not a single average pressure to do a comparison with. So I'm going to simplify this model. I'll put 1 layer. It's a radial model. We'll put 100 millidarcies in each one of these. Say the KZ is the same as, we'll just say this here. We've got 200 Fahrenheit, the US properties, initial pressure. Is that equal to the dew point? So let's give it some initial pressure higher than the dew point. Give it 5,000 initial pressure. So we'll have some of this undersaturated performance. We can use, the way it's set up now, we've got a surface separator that's got 46.5% of this component here going into the stock tank oil, and 100% of all these components going into the stock tank oil. It's called a split factor table instead of using an equation of state separator flash. So we'll use that. We'll have to use the same kind of factors in phase comp, and I'll show you how to do that in the simulator to create something we call a stock tank oil or oil C5 plus. And then this perforation is just, we don't need K1 to K2 since it's only a single layer. The well's there. Producing at some rate for 10 years. We'll probably take that longer. Actually, we can, just to make sure everything's running, we'll just run it for a year just to see what happens. Is it clear? We got a radial model. We've got some kind of rel perm. I don't know. That shouldn't make any difference from what I'm telling you. If the only oil that produces practically is coming from the gas carrying, then the relative permeabilities don't really make any difference. Okay.
Last year we tried it and didn't affect actually. Last year
you tried that, yeah. So we can do that, and then we'll have to take and convert this into phase comp. That should be fast. Yeah, so I don't think there's anything special about this. We'll just run it. In fact, to begin with, we can just stop the simulator. We don't need to run it at all, just to see the initial gas place and initial oil in place, just the initial gas-oil ratio, because we want to get that to be the same in our PVT program, our simulator. Okay, so I'll just save this, and I'll try to run this data set. I have to go over and make sure I've got the right. I think that's right. Search initial. Okay, so we got initial GR of 7,228. We want to get that. We've got a warning here with oil viscosity is unusual, so we'll have to see what's going on there. We've got saturation pressure. Let's see, why is the... Oh, it's doing a bunch of... okay, let's just go up here and search for saturation. Maybe dew point. Okay. So we've got the 3480 dew point. We'll have to make sure our simulator, PVT simulator, gives the same. We want the same properties, densities, viscosities, and K values at the saturation pressure. So where's the saturation pressure K values? That's here. Okay. So we've got enough stuff coming from the simulator to make sure that when we go and bring this into the EUS simulator phase comp, we should get the same saturation pressure, the same K values, the same densities of gas and oil, same viscosities at the saturation pressure. And if we don't, then we've done something wrong in taking the EUS and composition from one model to another. Okay? So let's take that. And what I'm going to do is I'm going to take these properties here into the okay, so we'll do a US text file just to get it all in there. I'm going to bring these in to Excel to make this a little more easy to... We don't need the omega A and B's, but we do need these here. I'll put this up in the same there, and then we can bring those numbers in. I'll do it in Excel. Like that. You guys see this okay? Okay, and then we need some units. I'll just make this in the, this is Rankine, I think. I don't need these. This is a centric factor. In phase comp, this is called AF, volume shift, and ZC this. Those are the Okay. Make sure we got enough digits. We look the rightmost is 0 and get rid of it. Rightmost is 0. Okay. We've got this is the characterization. We'll just call it, it's ARCO US, Pang Robinson US, something like that. Maybe just ARCO SB3 US. And the OS that we're using, I think it's Pang Robinson, is that right? And then we need the binary interaction parameters from that file down here. Into here. That doesn't look good. That was not good. Minus 0.02. It's actually the same one as here. That. Make everything look a little bit cleaner. How far do we need to go? We still got some non-zeros there. That. Okay. Yeah. And then we've got, what else do we need? Some kind of composition. Like here. This composition here probably has more digits than that's what we need. Point. There. How about format that like that. I'll show you a little different way of inputting compositions into face comp than we did yesterday. It's a little safer. You put the component names here like that. See, like so that we get okay. I'm going to say mix gas condensate, and we'll say it's in moles just to clarify. Okay. So we've got a tank called GC, is that right? And it's filled with these moles. And now we should be able to do some calculations like saturation pressure. That's the first one. So we do a mix feed that says fill the PVT cell with a tank, the gas condensate. We'll use 1 mole of that. Okay, and then we'll set the temperature to, what was it, 200 Fahrenheit, I think. Don't need so many digits there. And then we'll do a saturation pressure calculation. Okay. And I'm going to save this before it crashes the whole system. Okay. So we can put in Untitled, just to have one. SP3 ARCO EOS compare with sensor results. QC. Curtis. In class, February 2012. Okay. And then we got the characterization. And we have all the properties we need. We've got molecular weight, TCPC eccentric factor, volume shift, critical Z factor. For the viscosity, we've got the binary interaction parameters. We've got a composition. And then we'll do a saturation pressure calculation. And from that, it will give us some K values and things we'll compare directly with. This we don't need to keep. We'll compare directly with these K values. And then we need some properties, viscosities. That's not printed automatically. So we'll do a, we'll ask for that here. We'll do another experiment. CC experiment. Give it an ID. Get saturated phase properties. Pressure. Let's see. Stage. Okay, and then we can get. We want liquid density, gas density, liquid viscosity, and gas viscosity. Those are the main properties that we want. Stage 1. Let's see, we need pressure, we need units, and the units I think used by sensor output is what? That's pounds per cubic feet in centipoise, so we need pounds per cubic feet. Stage 1 and okay, so that's the experiment for okay. Are there any questions? What it'll do is it'll take from the saturation pressure, it'll fill in that pressure. It's kind of nice also to have we'll just print the temperature. It's not Fahrenheit. So it'll actually give, for this saturation pressure and temperature, it'll give us the liquid density, gas density, liquid viscosity, and gas viscosity. And then we'll use those to compare with the sensor. And the K values will be printed out when it does this. So we'll compare the dew point and the K values. This, if you ever do compositional reservoir simulation, if you ever get into this area as an engineer, what we're doing here has to be the first thing you do. Okay? Otherwise, it was a waste of your time to come to the university here and have me using my time. This is what I do. This is what all of my engineers do. This is what Keith Coates does. Any good engineer has to do this, to double check that from the one model, PVT SEM, to your Eclipse 300 or your CMG to PVT prop, inevitably through all the cuts and pastes and choices and radial bars that you have to click, something will be wrong. and you have to find what's wrong. And if we get it right first time, I'll be disappointed because it won't show or reflect even my having done this 100 times before. There's always some little mistake you don't think about. Okay? Now we're doing it a little bit opposite. Usually you have a PVT sim program and you have an equation of state from that and you're going to a reservoir simulator. In this case we're going the opposite direction. It doesn't matter. Okay? The process is the same. And the tedious, boring, checking the numbers and doing all these things, that is why you became an engineer. It's not to point, click, and run the simulator and go get a cup of coffee. Okay? So let's do this. So I'll copy all this into a text file here. We'll call it US phase comp. Paste it in, save it, and run it. Hopefully we'll get something wrong. I don't have to do that. I can just double click on it. It'll run it. US out. Take that away. Okay, so then we go through. You guys are not real familiar with phase comps. We just kind of see what it says. It repeats the stuff that we put in. We put in PSI-A, Rankine, molecular weight, eccentric factor, all these things. It's got the Pang-Robinson equation of state. It's got binaries. Hopefully they're right. I mean, what I would do if I see any discrepancies in the calculated properties, I would start checking. But usually I'll check the numbers anyway, just to do a double check. So I'll sit there and take this output from phase comp. And then the output from sensor, I'll go to the properties table, start looking at those, looking at binaries so we can go back and forth. I can do it with my eyes a little bit faster than you just to double check some of these things. And if I don't see anything there, we've got the compositions. Those sum to 1 because you read in moles. Then it calculates internally mole fractions. So we didn't type an extra 0 or something in there. It does sum to 1, so that's a good sign. And then it's got saturation pressure in bar. I don't really want that, so I'm going to go change the units here. Somewhere here, I'll have to tell it to use units of. Well, actually, it comes in the next table. So. Let's see here. Down here in the CCE, it fills at 3481. Okay, 3481 at 200. So let's go look at the output from sensor. That's the output from sensor. We have to look for dew point. That's the wrong dew point. 3480.8. 3480.8. Again, unfortunately, it's too close. You get the wrong impression. We got 26.58 pounds per cubic feet. 26.58. We've got 19.13. 19.13. Viscosity 0.073. 0.072. 0.037. Well, okay. Unfortunately, everything worked this time. Don't think it's going to be that way. It's just because it is a lucky day. Okay. Now, gas oil ratio we don't have from the PVT simulator because you can't give in this PVT simulator. You can give those recovery factors as a process and have it create black oil tables with that process. But you can't have it do a separator experiment using recovery factors. So I would have to create a black oil table. There's a lot of stuff I'd have to do to get the right gas oil ratio. From the black oil table options of phase comp, it's a headache. You have to do it. It creates black oil tables, but not in a straightforward manner. And instead of me going in and trying to figure out how to get that in phase comp, I'm not going to do that. But I'm going to calculate the gas oil ratio myself for a given recovery factor set of tables. And the way I do that in phase comp is I can go up here and I can define, as we did in the sensor data set, a C5 plus component. Okay? So let's go back to here, and I'm going to find my process. We're going to define a process with component liquid recovery factors. Okay. And the way that basically works is that you say that you come in with a well stream, molar composition here with the number of well stream moles. Okay. You put it through this process, and you end up with moles of surface gas and moles of surface oil, which is defined as the moles of the well stream, moles of well stream composition, molar composition, times the recovery factor values here, from 0 to 1. Each component. So you say 100% of the heaviest component goes into the oil. Okay? And those factors are different for each component. And those factors are defined in the input data set of sensor, which we'll open up again here. Here. These number here. So it's 0 for all the components until C4 to C6. And of the C4 to C6 component, 46.5% is going to go into the surface oil. Okay? So we can define in our phase comp file, somewhere if we can find it here. Lump. We're just going to call it gas, or surface gas maybe. Maybe gas will be misunderstood. Surface gas. That will be all of CO2, nitrogen, C1, C2, C3, and 0.5. What was that number? Well, that's the amount that goes into the liquid. That's going to be lump surface oil. That's going to be C4, 0.465. Is that what it was? And then 1, 1, 1. Here, it's going to be 5, 3, 5. Is that right? Hopefully it'll print this out and it'll show us the numbers, so we'll make sure we've done this right. Okay, so let's just try that. Let's just rerun the phase comp file and see if it interprets that correctly. Files. So we'll go up the top and see. Okay, so you see it's got new lump fraction definition. It's all of the CO2, and then it's 53, so it gives the number there, and it's that much of that and all of those. So that looks right. Okay. So then what we can do is that we can create a PVT experiment to check the initial GOR. How should we do this? We need it to calculate the density and molecular weight of that surface oil for us. So we need to create a mixture with the surface oil. Let's see here. Okay. Okay. Well, if we get the let's see. So the question is how to get the gas-oil ratio from this. Okay, so the gas-oil ratio will be the moles of gas, right? Pound moles, let's say, times 379, right? That's standard cubic feet per pound mole. Divided by the moles of oil times the molecular weight of that oil divided by its density, right? And then we have, that's going to give it us in cubic feet, right? If you use pounds per cubic feet, pound moles and so forth. So if we take that mole, we've got to take that cubic feet and divide by 5.615 cubic feet per stock tank barrel. All right.